Okay. Oh my goodness, what a disaster today. So I went through the IT help and they said to use the Ethernet cable. I plugged that into my computer and now my computer cannot even connect. Or it connected, but nothing worked. So now I'm on the desktop here and there's numerous files that I need to get to that I can't. But anyway, I will do better next time. I'm sorry? Yes, yes, I am. I got that going, I think. If not, I'll do it again tonight. Okay, so we finished up this example last time, so this just kind of sets the stage. So we finished this, and we went through all of this. So that should be recorded and posted. Okay, so the rest of this chapter is going to be a bunch of related, but kind of like individual topics. Like a special case, what do we do? Well, we're going to define specific heats. What do we do if we're looking properties for liquids? What do we do when we make a incompressibility assumption, et cetera, et cetera? And I wish I could make this more interesting, but it's just kind of like basic information. We get to the fun stuff later on in thermo when we start doing cycles, power cycles, refrigeration cycles. I mean, for mechanical engineers. That kind of stuff should be fairly enjoyable. But at any rate, so you're just going to have to bear with this portion of this course. It will, I think, be a little more fun towards the end. But this is just information that you have to fundamentals. So anyway, specific heats. So we're going to define three properties related to specific internal energy and specific enthalpy. And they have all kinds of applications, and you use specific heats all the time when you're doing thermal type calculations. So, you can see we have mathematical definitions up there. CV is the partial of internal energy with respect to temperature at constant volume. So that's what that little V is to remind you of, that the assumption is that volume is held constant when the change in internal energy is evaluated. And so we will actually use this in a lot of cases. We can assume that CV or CP, whichever we're working with, is constant. And then you just kind of say, well, we're gonna forget about the volume. A lot of times the change in internal energy doesn't change very much with respect to volume, and so you just kind of forget about that, and you make that a derivative, and so then you've got CV is equal to du dt, and then you can multiply across by dt, and then you can integrate to get a change in internal energy. And if CV is constant, which is, fairly nice to assume a lot of times, if your temperature range isn't that great, you can assume it's constant. And then all of a sudden, your delta U, small u, if it's per unit mass, is just the specific heat times the delta T. So that's kind of where we're going. But, we got to kind of present the mathematical formulation of it and how it's defined. But so if you think about it, what internal energy is what? I mean, it's energy per unit mass. And so this is, how does energy per unit mass of a substance change with respect to temperature? So, if I have some substance here and I double the temperature of it, well, how much has the internal energy changed? And this is a physical property or a characteristic of that substance that lets us calculate, put hard numbers to it and figure out how much that internal energy changed as a function of the increase or decrease in temperature. So the practical applications of these are, wide ranging, and, once you get used to them, they're really very, very easy and friendly and helpful to have around. Okay, so the CV term, we've already been over. CP is the specific heat at constant pressure, and it defines the enthalpy change with respect to temperature at constant pressure. Okay, so what you got to remember is if you want an internal energy change, you want to go for a CV. If you want an enthalpy change, you want to start looking at CP. Okay, and then K, specific heat ratio. I don't know if you've run across that, but it gets used all over the place, and it characterizes different gases, different materials, liquids, solids, whatever. And it's just the ratio of CP over CV. For air, you know, air is famous, the number is 1.4. And of course, these things, you know, these CV, CP, and K values will change as a function of temperature as well. And so I've stuck some plots in here, and there's always plots in the textbook and all of that. So, you know, the other thing you need to get set in your mind, if you have a problem that's over a fairly small temperature range, which might be defined as a couple hundred degrees, you know, it's probably not bad to assume this is constant. Well, I have some plots here. If you're going over 1,000 degrees or 1,500 degrees, whichever system you're in, that's too much. And so then you have to take in the variation of specific heat with temperature into your analysis. You don't get out so easy. It becomes a little more complicated to evaluate. The concepts are the same, but you have to put a function in, or some, you have to go to a table that has allowed CV to change over large temperature range as it's evaluated to get accurate data out of it. Okay. In general, CV is a function of specific volume and temperature. And, you know, since volume can be thought of as a function of pressure, you can think of it as pressure, but that's almost misleading. You know, in general, we always think of CV as a function of specific volume and temperature, and CP depends on pressure and temperature, even though you can make the argument the other way. But I see no point to do that other, you know, but anyway, the authors do. Specific heat data are provided in figure 3.9 and tables A19 through A21, which I was going to put up there, but since all of that is on my computer, I don't have access to it. I guess what I'm going to have to do is to get a big flash drive and load everything and try to work off this computer, which the system seems to like a little bit better. Anyway, you should look at those tables. I have cut and pasted portions of it. Hold it, I'm getting, what is this? I'm getting an email. Oh, okay, never mind. All right, I thought that was in relation to this transmission today, but it's not. Okay. Okay, although CV and CP are referred to as specific heats, there's not a general relationship between them and the heat transfer term and the energy balance denoted by Q. So this is kind of FYI. Okay, so I cut and paste, I scanned that out of the book. I don't know that that one's in the tables. Maybe it is, I didn't find it. But it gives you an idea, oh my, if you've got a big enough temperature range, there goes specific heat, CP, that's CP. In US units, it's what, BTUs per pound mass per degree Rankine. And you can see, and this is for water, and so that's water vapor rather. So you see that saturated vapor line is the vapor side of the saturation dome, and so you can see how specific heat changes on that line and then out into the superheat region. And of course, I mean, but look at those pressures. I mean, those pretty significant pressures. You know, I mean, the first line is 200, so you know, and there is some variation. as a function of temperature if you stay at 200 and then vary the temperature significantly. So it just depends on the range that you're trying to work, really, how much the variation in specific heat is going to be. So, and notice the units, BTU, that's energy, and it's per pound per degree, okay? So, the old number that I always remember for water, in US units are nice, the specific heat, CP, which would give you an enthalpy number, is 1. Okay, so that says that it takes one BTU is the amount of energy it takes to change 1 pound of water 1 degree Rankine, but the size of a degree Rankine is the same size as a degree Fahrenheit, right? It's just the scale is changed. So if it's a delta T, and that's another point you need to think about when you're using these things, they're always defined in terms of absolute temperature. But let's say I've got 100 degree Fahrenheit temperature increase. Well, it doesn't matter. I can convert it to Rankine and subtract, and I get 100. Or I can leave it in Fahrenheit and subtract, and I get 100. So now, if it's an application where you're only going to use one temperature, oh, that makes a big difference. If I put in 100 or I put in 560, I get a big difference. But if it's a temperature difference, then it doesn't matter because the conversion factor cancels. You've got one temperature minus another temperature, and so the conversion factor just cancels out. So you've got a positive and a negative value, so it goes away. So, as long as you're doing a delta T, you can go ahead and put degrees Fahrenheit in it or degrees C, whichever unit you're using. But if you're putting in one temperature, you better be very careful. Most of the time, if you're putting in one, using absolute temperature is the right way to go. Okay? All righty. We may come back to that. I don't know. We'll see. Okay, approximate values for specific volume, internal energy, and enthalpy at liquid states can be obtained using the saturated liquid data. Okay, so this is a very handy approximation. So in that little diagram, it's a little confusing at first until you figure out what all of the lines are. So let's go over the diagram here first. So, it's temperature versus specific volume. That's our TV diagram. And this line right here is just the liquid, saturated liquid line of the saturation dome. Okay, so over here is two-phase stuff. And on this side is compressed liquid stuff, okay? So that's all that darker red, whatever it is. And then this lighter colored line is an isobar, okay? So that's a line of constant pressure. So we're coming up and then we've got a line across here, which is a line of constant temperature, okay? So at this temperature level, if we're on that dot right there, that's the saturation condition. Okay? That's just saturated liquid water. And we can go to the tables, and if I could get to the tables, I would, but I can't, so I'm frustrated. But I'll get over it. And so whatever temperature this is, you can go to the saturation tables, and it'll tell you what pressure that is. Okay, but this pressure is higher because this pressure doesn't hit the saturated liquid line until up here, and that's obviously at a higher temperature. Okay, so if I take this temperature on this line down here and go out to this pressure, then that's compressed liquid or subcooled liquid, whatever you want to call it. Okay, and so the purpose of this discussion is to show you that unless this pressure is tremendously large compared to the saturation pressure here, that you can look up these properties at the saturated liquid condition and use internal energy, specific volume, and a lot of times enthalpy as if they were saturated liquid at this temperature, which can be pretty handy because what you're going to find is when you go to the compressed liquid tables, that first pressure might be 500 psi or 1,000. And the reason for that is the numbers don't change very much for a given temperature until the pressures get tremendously high. And so, you're not going to put a listing in a table that's like 0.1% change from the saturated number. So you got to get that far away in terms of pressure before you get enough of an increase that it's worth putting in the table. So when they build the tables, that's what they do. And so what we're saying here is that, especially for these two properties, and we'll get enthalpy up here in a second, whereas we know specific volume is a function of temperature and pressure, it is very strongly a function of temperature and very weakly a function of pressure. And so, in fact, it's so weak that if that pressure is anywhere in the ballpark to the saturation pressure, we can just look up properties at the saturation temperature. Now, how can you manage to screw this up? You can look up the saturation properties at the pressure and not the temperature, and then you get a radically wrong number because these things, these properties, internal energy, specific volume, are very weakly a function of pressure. Okay, so if you're in a hurry or if you're within 100, 200 psi, you can just go to that saturation table, which after you get some experience with this, that's the table that you are most comfortable with because that's the table that you use the most. You're always going to those saturation tables. Okay, so that's what this discussion is about, and they're showing you, and of course this is not to scale, unless this was a huge pressure, these 2 points would be almost right on top of them, of each other. And I ran some numbers, and let me see, I can read them to you. I did a little spreadsheet that I was going to give you, but since I can't project this today, let me open that up here. Excel. Okay, so I got my little calculator up, and I said, okay, I just picked a temperature. I said 300 degrees Fahrenheit. And so the pressure, saturation pressure is 67, and the internal energy is 269.5. 269.5. And the specific volume is 0.01745 out of my calculator, which will be close, but won't exactly match the tables in the back of your book, but it'd be pretty darn close. I said, okay, so I'm going to keep that temp because I have to keep the temperature the same. I said, okay, well, let me make the pressure 300. Just, pick a number. That's, like 233 degrees away. And the internal energy changes by 0.12%. 0.12%. So for many, many analyses, I mean, you don't know the numbers that you're putting in with that degree of accuracy. So what difference does it make if the internal energy is off by that amount? And in a lot of cases, it doesn't. Okay. I said, well, okay. And then the specific volume was off by 0.0 0.99, less than 0.1% for a difference of what, 230, that's 233 psi. I said, well, okay. So that bears out what we're saying here. So let me go to 1,000 psi. So, you know, the saturation pressure is 67, and I'm going to put 1,000 psi in my calculator at 300 degrees. I'm going to keep it right there. And on the internal energy, it's off by 0.47%. Less than 0.5% error. And it's 900 and what? Is that 63? My math is not really good. 933, I guess. Yeah. Anyway, 1,000 minus 67 is the difference, and it's less than 0.5% off in terms of internal energy. Okay, and on specific volume, it's off by 0.39%, even less than the internal energy is. So, you know, you see this bears out pretty well. Okay, an approximate value for enthalpy, H, at liquid stage. Now this is liquid, okay, this isn't gas. So say we got all these little categories here that you got to remember. This is in terms of liquids. Okay. So approximate value of enthalpy at liquid stage can be obtained using those two equations and just the definition. And so enthalpy is internal energy plus pressure times specific volume. And so this little equation in black over here, so you know what they're saying is enthalpy, we know in general, function of temperature and pressure. Well, so we can take the temperature and go look up the internal energy, forgetting about the pressure, unless it's just tremendous. That's kind of the assumption that we're doing up here. And then we can look up the specific volume at that temperature and multiply by the pressure. And of course, I got to be careful on my units, right? Because I'm going to have to throw some conversion factors in there. Because I was thinking about that in terms of, I think in terms of US units. So, you know, that specific volume, is what? It's volume per unit mass, so it could be meters cubed per kilogram, or it could be feet cubed per pound mass. And then that pressure in US units is going to be what? Pound force per inch squared. So I'm going to have to get the inches out of there. So I got to multiply by 144. And then that's going to give me what? Foot pound force. Yeah, foot pound force. And then I got to divide it by 778 to get it into BTUs, if that's what that's most likely what the internal energy is going to be in. So, you know, when you use these equations, be careful on your units. You can't stress it enough. You know, that's why the Hubble telescope was blind when they put it up. Somebody didn't do a conversion factor. $350 million, and it couldn't see across the galaxy. I mean, it couldn't see to its wingtip. It was so blind, and they had to recut the mirrors. Anyway, who got fired for that? You know, I wonder. I bet there was a whole lot of this going on. Anybody ever been in the contractors meeting associated with construction? I used to do some HVAC design, and you get out on the job site and there's some big problem, and you have this big powwow, and everybody kind of stands around in a circle, and the lead contractor's there, and there's the mechanical and the plumbing, you know, all the different trades are around, electricians and all, and they start talking about this big problem that developed and how it's costly and somebody's going to fix it. And they all start looking at each other, and everybody goes like this. Oh, no, that's not mine. No, I didn't have anything to do with that. Somebody has to buck up to fix it. Anyway, okay, so we got equation 313. So enthalpy function of temperature and pressure, can be approximated. So that would be the enthalpy. The little f indicates that's saturated liquid at the temperature. Just go to the saturated liquid table at the temperature. And then also while you're there, get the specific volume. And while you're there, note the saturation pressure at that same temperature. And then whatever pressure that you have, if say it's 1,000 or whatever, then take that delta P times the specific volume, get your units correct, and you can get a pretty good approximation of enthalpy from that. Okay, and so he's saying that correction term, you know, with specific volume and pressure, a lot of times is very, very small and can be neglected. So then it's just a straight lookup. Okay. Incompressible substance model. Is there such thing as an incompressible substance? What?
Any liquid, pretty much.
What? Louder?
Pretty much any liquid, right?
Doesn't change at all? You sure it doesn't change at
It
all?
doesn't follow the ideal gas law because it's incompressible.
I'm telling you, in reality, there is no incompressible substance. You take water. Well, I mean, I would pull up the tables, but I can't, and put it up for you. Look at the specific volume numbers for liquid water as you change pressure. They change. I don't change a lot, but they change. Everything. I sit here, I push on that thing. There is a movement on those molecules. It may be so small that you can't measure it, but there is an impact, there is a movement in those molecules. You know that steels creep over time if you get them above a particular temperature. You ever heard of creep deformation and damage? You take a steam turbine rotor, get it above 800 degrees Fahrenheit for a long time, and those materials actually flow. Now, they don't flow very fast. They don't flow fast at all, but they flow. They talk about the metallurgists talk about in the creep regime, metals flowing. I mean, it might take 10 years for it to move, you know, so many nanometers, but it moves. And things can diffuse through the matrix and all kinds of stuff goes on. So in reality, there is no incompressible substance. However, I do have a story. I've got time for this. You know the difference between an engineer and a physicist? Have you ever heard this? This is a joke. You are supposed to laugh at the end of it. I'll get you primed up here, okay? I know it's hard to laugh in a math. So, I don't know, they were at this party, and they had this kind of game set up. And there was this beautiful young woman like on the other side of the room. And there's an engineer and the physicist over here. And they were both kind of looking at this young lady, and they had an interest. They'd like to meet her. And so, but the way the game was set up, they take turns, but they could only go half of the distance from wherever they started to this young lady in each turn. And they asked him, okay, do you want to play the game? And the physicist said, well, no. No, I don't want to play. They said, well, why? He said, because I can never get there. I can never get there. And they asked the engineer, and he said, yeah, I'll play. He said, well, you can never get there. I can get close enough. So anyway, please don't report me. I have to be careful which of my old stories I tell these days. Sometimes I might offend somebody, but anyway. So that relates directly to the incompressible substance model. The physicist would say, no, there is no incompressible substance. The engineer says, within any reasonable realm of calculation, it's more than fine to assume that it's incompressible. Okay. So it's just a question of, you know, different fluids will compress different amounts given the same pressure difference. You know, it's a characteristic of the fluid. Oil is going to compress more than water, and you know, molasses will compress more or less. I don't know the exact numbers on all this stuff. Okay, for a substance modeled as incompressible. Okay, so modeled as incompressible. So once you make that assumption, and see, that's part of this structure on solving problems. You write up there what's your model. Assume incompressibility. And then all of a sudden it puts you into these equations. Whereas before you really couldn't use all of the equations here because you had not made that assumption. Okay, well, specific volume is constant, and so and that's 1 over density. So you know your density, what your cubic foot, pounds mass per cubic foot. Yeah, that's going to stay the same. So you can press however hard you want to, but you can't move the molecules closer together or further apart. So that makes internal energy only a function of temperature. Well, we already showed that it's, you know, not a very strong function of temperature. I mean, of pressure at all, but it is strongly a function of temperature. Okay, for a substance modeled as incompressible, Cp equals Cv. Ah, well, that's handy. So, you know, if you're working with water or something like that, and it's going to stay in the liquid state, well, just, you know, invoke incompressibility, and you don't have to worry about Cp, Cv. And with that assumption, you drop the subscript, and it just becomes C by itself. So in the book, if you see a specific heat written without a subscript, that will tell you that they have made the incompressibility assumption. It probably said it, but you know, it's hard to read all the words in a textbook. You know, you might have skipped over that part. Okay, for a substance modeled as incompressible with constant C, then a change in internal energy, so that what they've done is that's that du is equal to C dt, and they integrated from 1 to 2. The C was constant, it pulled through the integral sign, and so you got T2 minus T1. Okay, so real simple. It's constant. Look it up in a table, multiply it by the temperature difference, and again, if it's a delta T, you don't even have to convert to Rankine or Kelvin. And then for the enthalpy, it's the change in internal energy plus the specific volume delta P correction on the end. And so there is only one C, there is only one specific volume because it's constant. And so, you know, then you know your pressures. And a lot of times, again, the same comment that last term in many, many cases is small enough and we can ignore it. Okay. Incompressible substance. Okay, so I stuck, yes.
Can you go back to that last slide?
Yes, sir. Take your time. Anytime. If I start rolling too fast, just throw a lasso on me. Yes, sir. Okay, so I threw this in because it's interesting. The order they do things in this presentation seems a little screwy to me, but you know, nonetheless. So we all remember the ideal gas law, right? Pressure, total volume is equal to N, and N is what the number of moles. And if it's 6.022 times 10 to the 23rd, it's gram moles. So we got to be careful with that because with that particle count. But we can work in kilogram moles or ton moles or pound moles or whatever designation of moles we want to. But the 6.022 times 10 to the 23 is only for a gram mole. There you go, number of particles in 12 grams of carbon 12. So they kind of, and then the ideal gas law we can look that up. It has a bunch of different values depending on what system of units that you want to work in, and that's listed in the conversion constants page of your tables in your textbook. Temperature, if we're doing SI units here, so that's going to be Kelvin. Volume could be liters, could be meters cubed, and pressure could be all of those. Just it depends on, you can get different values of R for different units, and you just have to make sure your units are consistent. Okay, so that's P, total volume, number of moles. That R in that equation is what we would call the universal gas constant. Okay, and temperature. Okay, now we can divide through both sides of the equation by N, in which case that V would become a small v with a bar on top in your textbook's notation. So this is not out of your textbook. I just grabbed it from Google Images just to have something to throw up there. So if you divide through by the number of moles, then you have a molar specific volume. So it would be meters cubed or liters, whatever your volume unit was, per mole of substance, whatever substance you have present, of gas or, yeah, okay. We can also work with this in with units of mass, where we take the molecular weight and we take the universal gas constant and divide by the molecular weight. We'll show some of that later. And it becomes a specific gas constant, because if you're working with carbon, you take whatever universal gas constant, divide by 12. And that changes the units in that from moles to kilograms or pounds or whatever your mass unit is. And then the N turns into an M. So just we'll review all of this in some detail. But anyway, I wanted to throw that up there. But so that's the standard ideal gas law. P little v is equal to RT, or P big V is equal to nRT. And I think you all are familiar with that from good old days in chemistry and high school and all that kind of stuff. Okay, well, you probably, have y'all seen a compressibility factor chart? Is this the first time y'all have ever seen a chart like this? I kind of think so. Yeah, I don't think they do this in chemistry. Well, it turns out that if you really look at a wide range of pressures and some pretty high temperatures, that this relationship doesn't always work real well. And so this Z, this compressibility factor, is a fudge factor that is basically measured and correlated, that you pull off a chart like this and you include that. And so you see that Z, it's P. Now, this nomenclature is out of your textbook. This is out of your textbook. So Z is equal to pressure times the molar specific volume divided by the R bar, which is the universal gas constant, times temperature. Well, and look at Z. Well, okay, so up here, what is Z? Well, it doesn't show up, so it better be 1, right? So up here, Z is 1. Well, you come down here and you go, holy moly, this thing's not good. This thing, and so there's some cases where this is not real good. When you get a value of 0.2 or 0.3 for Z, that says that PV is equal to ZRT and Z is 0.3. I'd say that's a pretty significant error, you know? So that's what this is all put together to kind of show you. And you can work problems and you can pull values of Z off of this, a plot like this, and there's some better plots in your textbook. I mean, these are from your textbook, but there's some in the tables that are better to use, okay? But we need to look at the different parameters. So reduced pressure. So what that is, that's your pressure divided by the critical pressure. You know, that, you know, on the saturation dome, we got that little dot up at the top of the dome. And that pressure up there, that's the critical pressure. Okay, that's one example. But, you know, you can look up in tables, you can look up critical pressures for all kinds of substances. Those are readily available. And I've got I've got some out of your book. I'll show you here in just a second. So that's what reduced pressure is. It's your pressure divided by the critical pressure. Well, and you see, so we get down to zero. Well, at zero pressure, these things all run into one. Now they don't show it right here, but theoretically, these things all run to PV is equal to MRT at absolute zero. But you can see, so I mean, from absolute zero up to reduced pressure of 1, which is the critical pressure, I mean, that's just a small portion of this. So these are really high pressures in general. Now, it depends on the substance as to how high the critical pressure is, but these are significant. In general, a reduced pressure of, you know, 3, 4, 5, 6, 7 is pretty darn high pressure. And, you know, so there's probably not a lot of applications for gases at that higher pressure, but there's some for sure. Okay. All right. So, well, if that's reduced pressure, what do you think reduced temperature is? Well, guess what? It's the temperature divided by the critical temperature at the point that you're interested in evaluating the Z. Okay. And so you see, so we've got down here at TR equals 1, this bottom curve, that's the critical temperature. And in general, that's pretty high, okay? And then it goes all the way up to reduced temperature of 2, or twice the critical temperature. And you can see a lot of gases follow these same curves. See, they've got, what is there, 10 common gases. Methane, CH4, ethylene, I'd have to look it up in the table. I can't, it's a C something H something, I know that. There's nitrogen's in there, carbon dioxide, water vapor, all this. And so people over the years have taken lots of data on this, and this stuff has gotten correlated in this fashion. Okay, so correction factor, known as the compressibility factor, from a generalized compressibility chart, generalized because it's got 10 different gases on it. Okay, questions? Interesting. Okay, so what causes all of this variation? We haven't talked about that a little bit. In the ideal gas model, how are the molecules considered? How are they modeled? Do you know? It's like the conceptualization of the ideal gas law is like all these molecules are like little steel BBs out there floating around in space, little bitty ones. And they just, boom, they run into each other, and they just have the elastic collisions. And so that doesn't soak up energy when they collide. It hits the wall, bingo, like throw a steel ball up there, and that wall doesn't absorb much. It's got a perfectly elastic, you know, response. And the molecule comes in and goes off, and they're just out there banging around in space with no interaction. Well, if molecules are pretty spread out at low pressure, that's pretty much true, you know, and that's the assumption behind the ideal gas law. But if you start increasing pressure, what are you doing? You're forcing all these molecules up next to each other. It's like, you know, instead of the next molecule being way down the hall, it's like right there. And all of a sudden, now there's some interaction. You know, I don't like that molecule. You know, he and I don't see eye to eye. You know, maybe there's fisticuffs or something, you know, but there's interaction between the molecules, and it changes the state relationship between pressure, specific volume, and temperature. Okay? So that's what's happening, and we call that real gas behavior. There's ideal gas behavior, and there's real gas behavior. And so if you go to work for a big chemical company and they're working on stuff at high pressures, you don't get to use PV is equal to RT. You don't even get to use PV is equal to ZRT. They've got equations of state this long. They have umpteen different terms, and I'll show you some in the next class or two. There's Redlich-Kwong, and there's van der Waals equation, and there's umpteen different. All these guys have different equations of state named after them because they went in the lab and they took all this data and they figured a way to correlate that into an equation. And they look vastly different than the ideal gas law because they incorporate real gas behavior. And so one of these equations, I've used Redlich-Kwong, can't hardly say that, and it's pretty darn good, but it's only good for certain types of molecules and certain gases. And so if you get out there in the literature, if you know what gas that you're trying to work with and model, you can look for correlations that are known to be successful for that particular gas and molecule. Okay, so they're just playing around with the equation. So Z is PV over RT. And again, the hats mean that we're working in moles. Okay, it's not mass, it's moles. And there's the definition of PR and TR. And so that's the same. So I don't think there's anything there we haven't already said. We'll restart. Okay, there's some of the units on the ideal or the universal gas constant that goes into these equations. You need to really become comfortable. I mean, I always remember the 1545. That's just a number I can remember. So when I'm doing ideal gas law, I remember, I'm in US units, I remember 1545. And the other thing I remember is if I got PSI, I got to multiply it by 144 because I got to get those blasted inches out of there. So whatever system that you tend to work in, it's good to get enough experience that you remember the pitfalls. Anytime you see PSI, man, that sets off a red flag. You better be reaching for your 144 to get rid of those inches most of the time. So the conversion from foot-pound force to BTUs is 778.17. So if you take 1545 and divide by 778.17, you get 1.986. So it's just a conversion factor away. And then on the metric side, sometimes you'll see that 8,314 joules per kmol. See what I'm saying? So you may see it with a different set of units as well. I mean that we already saw it in that previous table. Okay, symbols PC and TC denote temperature and pressure at the critical point for the particular gas under consideration, and those values come out of the tables that you have.
Equation 3.23, is that specific volume?
Is what now? Say that again.
Equation 3.23 for V, is that specific volume?
Is that what?
Specific volume?
Yeah, but on a molar basis. Because what specific volume is what volume, normally we think about volume per unit mass, but when it's got the hat on it, it's volume per unit mole. So yeah, you need to think about it. When you get those things with hats on them, you got to be careful because you're going to have to use the molecular weight. Say if I give you an amount of mass and you're going to work with that, then you got to take your mass and turn it into moles. Or if you're going to use a specific volume per unit mass, then you've got to convert that one from meters cubed per kmol to meters cubed per pound. And it's the molecular weight that's going to do that conversion. Because what are the units on a molecular weight? Say 12, carbon's 12. I can't remember many of them. I remember carbon. Carbon's 12. So that's 12 what? It's 12 grams per gram mole, 12 pounds per pound mole, 12 tons per ton mole, 12 whatever's per whatever mole. You know, make up your own unit. And what's happening is the size of the pile changes and the number of particles changes, but that relationship is still the same. So, you need to work through these units enough time, practice. Look in there's example problems in the book where they do all this stuff, but practice those units. Because, the general concepts don't confuse people that much in thermo, but all these little details of working the problem give you a problem with that little hat on there. And if you haven't practiced that, you're going to go, oh my God, oh, the hat, oh, what's the hat? I forget what the hat means. Well, if you don't remember what the hat means, you're, pardon the expression, screwed, as far as getting the right answer is concerned. Then you're just playing for partial credit. Okay, generalized, on with this. So P, PC, T, TC as specific, molar specific volume, and R are used in consistent units. Yeah, that's a good idea. And Z, okay, that's good. Z doesn't have any units. It's dimensionless. And these reduce pressures and temperatures. Obviously, it's a temperature over a temperature or a pressure over a pressure, so they don't have any units. Okay, for example, pick air, 200 degree K, and 132 bar. 132 bar. Now, that's a pretty high pressure. I convert everything to PSI, so I have some idea how high it really is. 132 times is 14.5, I believe. So that's 1914 PSI. Whew. That's a little on the high side, You don't want that behind that door when you go to open that door, right? No, you don't want that. Every square inch would have 1,900 pounds of force on it. It would be a problem. All right. So we've gone and we've looked up. So the critical temperature is 133 K. So you take the 200, divide by 133, and you get 1.5. Okay, and then for the reduced pressure, we got 132 bar, which is our pressure, and the critical pressure is 37.7, so we get 3.5. Wow, that's pretty easy. Shoot, I can even do that, I think. Okay, and so there's the curve that's for the reduced temperature, 1.5. And there's going up to that curve from a reduced pressure. And then you're going to read over and you get 0.8. Nothing hard about that. And then so then you use that 0.8 in PV is equal to ZRT. And bingo, you go ahead and solve the equation. Okay? And this is just showing, this is what I referred to before, that bottom equation, 325, that our hat is the universal gas constant and M is molecular weight, okay? So if you see, like in the equation right above it, Z is equal to PV over RT with no hats, then the units, we got pressure, then that's regular specific volume, feet cubed per pound mass or meters cubed per kilogram. And R is called the specific gas constant, which is the universal divided by the molecular weight of the gas that you're working with. If it's oxygen, it's what, 28.965, I think, something like that, is a weight average for dry air. And so, you know, you can do it on a molar basis or you can do it on a mass basis. If you're doing it on a mass basis, you have to adjust the gas constant with the molecular weight. That makes the units work. Okay? Not too bad. Okay, solid lines labeled with TR values represent best fits to experimental data. And like we said, there are 10 gases represented. There is little scatter. So it fits pretty well. At the lowest reduced temperature value shown, TR is equal to 1. Compressibility factor varies between 0.2 and 1. Less variation is observed as TR takes higher values. So, okay, we got all the little blue balls and they're all gonna converge over there. For each specified value of TR, the compressibility factor approaches the value of 1 as PR approaches 0. Do y'all know how to program that stuff? I don't know how to do that. I'm decent at Excel, but I don't know how to do that. That's.
I think you can do that with PowerPoint.
Yeah.
I think pictures.
I need to. Yeah, you know, you can learn to do almost anything on YouTube these days. You need to look on, YouTube's really good for Excel tricks and all that. Just Google, get on YouTube, and yeah, that's what I need to do is get on YouTube and Google, you know, how to do animations in Excel. And I'm sure there's all kinds of videos showing you how to do that stuff.
Tracing the function.
What's that?
I think it has to do with tracing the function.
Could be. I don't know. I've never looked for it. Okay. On more stuff on compressibility. Low values of PR where Z is approximately 1 do not necessarily correspond to a range of low absolute pressures. For instance, if PR is equal to 0.05, then 0.05 times PC is what P would be equal to, right? And PC values in the table. For example, if you had water vapor, the critical pressure is 220.9. That's like 3,200 PSI, 3,206 or something like that. So if you take 5% of that, you get 11 bar. Well, 11 bar, it's 14.5 times 11 times 14.5. So that's like 160 PSI. That's still significant pressure. Even though in this discussion, it's 0.05 of the critical. So that's what the reduced pressure would be. Ammonia, carbon dioxide, air. So what is that? That's, well, what, 14.5 times 2, 28. It's about 27, 28 PSI. So these pressure ranges value, well, obviously, range from 1.9 to 11 bar, which in engineering practice is not normally considered as low pressures. See, we start considering low pressures when you get much below atmosphere, and these are way above atmosphere, obviously. Okay, to recap, the generalized compressibility chart shows that at states where the pressure is relatively small to the critical pressure PC, where PR is small, the compressibility factor Z is approximately 1. So if you're really low pressure, it doesn't really matter if your pressure's low enough. You're going to be about 1, which is up there. Okay. At such states, it can be assumed with reasonable accuracy that Z is equal to 1, and then PV is equal to RT, like you're used to in the past. 3 alternative forms of equation 233 can be derived as follows. You know what? I downloaded this off the internet. I don't think, I didn't get the one. I'm going to download this thing again. Let me see, what file is this? Because I sent you out one this morning. Oh, that's it. Huh. No, I guess this doesn't seem to have the slides that I added. Oh no. I've had a hitch in my get along here. No, it doesn't. Oh, crud. What in the world? Hang on. I swear. Let's see, I am on. Well, it's going to work now, huh? This will take just a couple of minutes here. I apologize. I hate this stuff. Get out. Does this have? Yeah, here we go. Yeah, here we go. I don't know. Who knows? All right, so we looked at this one. I had this one, but somehow the version, I don't know, maybe I need to send this to you. I'm going to add some more to it. I'll send it out again. Okay, so this is this is table A-21E, and this is kind of interesting. So these are curve fits of how specific heat varies with temperature. Okay, and so you can integrate this, right? I mean, gosh, even I can integrate a polynomial. And if I can integrate a polynomial, I know you can integrate a polynomial. If you can't, we're going to send you back over to Bruner and let them torture you some more, and they'll send you back. But I know you can integrate a polynomial. So guess what? If you had, say, this one is CP, and there's a relationship that we'll show next time between CP and CV, where you can approximate a CV from a CP. And so if you have a large range in temperature and you wanted to change in, say, enthalpy, then you can put this equation in for CP and integrate in terms of temperature, and bingo, you got it. Now, you should look at the the units, if you look at CP over R, if you select them properly, that will be dimensionless. CP and R can, if you pick the right values, will have the same units and they will cancel. So see, that's kind of slick, which means they don't have to publish a whole bunch of different curve fits. But I suspect that if I can dig up a homework problem, I'll give you the joy of integrating this at least once, you know, so that you can appreciate all the times that you don't have to integrate it. And also, down at the bottom of the table, we've got note A for monoatomic gases, such as helium, neon, argon. CP is constant over a wide range, wide temperature range, and is very nearly equal to 5/2, or that's what, 2.5 times R. Boy, you need to note that, because I'm telling you, you'll get someplace and you'll be trying to do something for one of those gases, helium perhaps, and you go start looking at all the tables and you can't find helium. You can't find it. It's not there because of that footnote in that table. So sometimes that's hard to come up with if you don't remember that caveat on those particular gases. Okay, so that's something to note. So, you know, I mean, that's pretty easy. If you're trying to integrate what, CP dt from T1 to T2, you just got a polynomial expression with a bunch of constants on each term. So you got to do 1, 2, 3, 4, 5 terms, but it's still, it may be tedious, but it's not very intellectually challenging. Okay. And this is out of the SI units. It's the same, but the coefficients change because we're putting in degrees Kelvin K instead of degrees Rankine R. So you got 2 different tables depending on what set of units you want to be working in. This may be a little bit of an eye test, but this is the some selected specific constants or the specific heat numbers, etc. So you can see they give you some solids and the solids are at 540 degrees Rankine. So what is that? 6, so what is that? That's 80, isn't it? Yeah, that's, yeah, 60. Yeah, that's 80 degrees Fahrenheit. You got some building materials, brick and all that sort of thing. And so you got specific heat, density, and thermal conductivity. So you got all those. Insulating materials, and then liquids. So look at water. See, water is real nice. Down at the bottom, we got from 495 up to 720 Rankine, and basically it's 1. I like that. I can remember that. You can leave it out of the equation, except for making the units work, and you still get the right answer. That's nice. Okay. And there's the corresponding table in SI units. So for water, the number is about 4.2. What is that? Kilojoules per kilogram per degree K. So you can see the density numbers change a little bit with temperature. Not a lot. So that water is not completely incompressible. You just heat it up and it changes. Or you could push on it. Okay, so we went through all this. Let me see, I just wanted to hit the tables I put in here. I don't know, put that. I got one more here, yeah. I should get the right version. Okay, this is out of the generalized compressibility chart in the back of the book. Notice we have another parameter here. Look at those little crossing guys. We didn't have these little crossing guys before, did we? That's V prime sub R. That's the pseudo-reduced specific volume. and it's kind of interesting. There's the definition for it. Values of specific volume are included, as we just saw, on the generalized compressibility chart through the variable V prime sub r, called the pseudo-reduced specific volume. Now, man, you could drop that term at Thanksgiving around the dinner table, and you will impress the heck out of your relatives. Whoa, pseudo-reduced specific volume. Man, that kid's learning something. You know, your granny will go, what did you say? You know, your parents will puff their chest out a little bit and say, we're getting something back for that money we're spending down there at Tennessee Tech, you know. So be sure and drop some of these terms. Now, the downside is somebody might ask you to explain it. And so be careful before you drop it that you have an explanation. Now, you don't have to tell the truth because they're probably not going to know if you lie to them, but you need to have a story ready that, you know, something that'll fit in over a couple bites of turkey and some dressing or something like that. But anyway, this is, that's one of those terms. You just don't run into a good term like that every day. Pseudo-reduced specific volume. Well, son, what is that? Oh, daggum, I wish I knew, Dad. At least I remembered the term. Anyway, it's a correlation parameter. And so it turns out that using that formulation gives better correlation to the data than does just the regular reduced specific volume. Like we had reduced pressure and reduced temperature, we could do the reduced volume, which you see is just that's defined as the molar specific volume divided by the molar critical specific volume. But when they try to use that on the table, it doesn't correlate very well. So, you know, any crafty engineer is going to go, well, all right, we're going to get creative here. We're going to make up a new variable and try to find something that'll correlate better so that our nice little curves look nice and smooth and, you know, they look pretty. And so you can pull numbers. I mean, I know I hadn't taught thermal in a while, but we used to have a problem where you'd have to come to this table and pull this V sub r prime, and then you'd have to set it equal to this and get down here and solve for some numbers of pressure or something like that, whatever. I can't remember exactly how the problem went. But so you can, I mean, it's just kind of messy looking, but you can work problems with it just fine. It's just another parameter on the chart, okay? So don't let it throw you. You know, you just need to be aware that it has a different definition than you might suspect. That prime means that it's not just the specific volume divided by the critical. Okay, I think that's, what are we doing? I think that's probably a good place to stop. So we're going to finish up the lecture next time. We'll spend the rest of the classes working problems. So I'll just bring in some problems and we'll put them up, and then we'll go through the tables and try to go through step at a time to make sure everybody knows where this stuff's coming from. So I apologize for the hiccups. I'm going to figure a way to do this smoothly, but obviously we're not quite there yet.